All right, so yesterday we talked about vectors, some basic operations, addition and scalar multiplication, and the interaction between the vectors when we actually do these operations. All right, so yesterday we saw with vector addition, you move one vector on top of the other, and then wherever the resulting vector is, that's where, they add up to be. And then we had the scalar multiplication, which was like dilation in geometry, where we're not changing the direction. Well, sometimes we are. Maybe it's in the opposite direction. But we're really just changing the magnitude of the vector by multiplying it by what's called a scalar, some number. So here are 9 rules or properties that we have for vector addition and scalar multiplication. Now, I'm not sure how far you went into addition properties and things like that in algebra, but a lot of these should be somewhat familiar. All right. So for the first one, we have the additive inverse property. So all that says it doesn't matter if how you add your vectors. Okay, u plus v is the same as v plus u, and that's the same for numbers. Okay, it doesn't matter if you do 2 plus 5 or 5 plus 2; they get you the same thing. Right? But that is only for addition. That doesn't work for subtraction. Number 2, we have maybe the commutative property of addition. I forget the formal name. But again, like this, it doesn't matter what order you add things if you have 2 or more things to add. So here the parentheses tell you, remember parentheses tell you that you're working on that first. So if you do u plus v and then add w, that's the same as doing v plus w and then adding u. And you can even throw a third in there, and you can say it's the same as u plus w plus v. So again, as long as it's addition, it doesn't matter what order it's in, just as long as you complete all the addition parts. Our third one is the zero additive property. So 0 here is our 0 vector. Right? So it's just 0 comma 0. So if you add 0 to some vector u, you end up with that vector u. 4 is just a way to rewrite. It's the additive inverse. Did I say that? I might have said that. I forget. It's been a while. But we just move the u over. So if I add u to the opposite of u, and again, remember this, okay, negative u is multiplying your vector u by the scalar -1, which just makes your insides opposite, right? So if you took some vector u and added the opposite to that, you're going to get the 0 vector. Okay, and again, that's the 0 vector. That's a bold 0 there. Then we move to multiplication. So if I'm multiplying by scalars, if I have d times u and then multiply it by c, well, I can multiply those 2 scalars first and then multiply in here. Okay, so you can do that. Then we have 2 different distribution properties. Okay, here, if I'm adding 2 scalars and multiplying, it's the same as the addition of the products. Right, so if I add 2 plus 5 times the vector u, that would be 2u plus 5u. They're the same thing. They're interchangeable. And you have it as well when you're adding vectors. If I'm multiplying the sum of vectors by some scalar, then it is the sum of the products of that distribution, right? We distribute the C. These are just multiplicative, I think that's how you say it, properties. The unit vector 1 times u is itself u. The 0 vector, scalar. The 1 scalar times u is u. The 0 scalar times u is 0. Now this one is new and a little different. if you are asked to find the magnitude of a scalar times a vector, you're going to find the magnitude of the vector like we normally do, but now you're going to multiply that by the absolute value of the scalar. All right, so that one's a little different than what we've seen. And I will go over one example like that. Let me just take a quick look. Let me move this. So we're going to have some vector u is 1, 3, and 2u. All right. So we have our vector u, and I want to find the magnitude of 2u. Right. So first, I'm going to separate it like I see here. So 2u is going to be the absolute value of 2 times the magnitude of u. So now remember, the magnitude of a vector is just a single number, right? It's the distance, it's the length of the line, however you want to call it. And the absolute value of 2 is just 2. So that's nice. So the magnitude of u is going to be the square root of 1 squared plus 3 squared, which is the square root of 10. And again, remember, we're going to leave it like that. So the magnitude of 2u is going to be the absolute value of 2 times the square root of 10, which is just 2 root 10. All right, pretty straightforward. So the only thing you got to worry about is if this was a negative 2u, we'd still end up with the same thing. Okay, negative 2u equals the absolute value of negative 2 times the square root of 10, and we'd still get, 2 root 10. But I don't think you're going to see that too much. All right, so now for a new concept, vectors and the dot product. Okay, so we have two vectors, u and v. All right, so we have u1 and u2, and v1 and v2. So the dot product looks like this. It's going to be u dot v. Okay, it's like the multiplication symbol. Okay, sometimes it's a little bolder. Let me just make that a little cleaner. Yeah, nice thick. Not there. U dot v. Right, and so that is going to be a single number. Oh, that's too skinny. It's going to be the sum of the product of our vector components. So I'm going to multiply the x terms, the u1 and the v1. I'm going to multiply the y terms, the u2 and the v2, and I'm going to add that together. All right. So just one thing to notice is that the dot product results in a scalar, which means it's just going to be a single number. It's not going to be the coordinates with the triangle brackets. Okay. All right, so just like before, we have a few properties. I'll give you the properties, and then we'll take a look at a few examples. All right. So it doesn't matter the order that you do the dot product, u dot v equals v dot u, and that's how we say it, dot. Okay, you don't have to say times. Okay, it is the dot product, so you just say u dot v. Again, we have the zero property. So the zero vector, which is 0, 0, times, or 0 dot u is going to result in 0. Okay, and this is just the number 0. All right, so this is the 0 vector, and this is the number 0. That's supposed to be a number. All right, then we have the distributive property. All right, so if you are doing a dot product with a sum, it is the sum of the dot products. Now this one is interesting, and we'll take a look at an example. The dot product of a vector with itself is the same as the square of the magnitude of that vector. Okay, so that's an interesting one, and I think, yeah, we should have time, and I'll show you the math behind that. And then the fifth one is interesting. It's kind of like a distribution, but it's a little different. No, you. So if I'm doing the dot product and I'm multiplying that by some scalar, then I can distribute that to either the first vector or the second vector. All right, so here you're not distributing it to both, it's going to one or the other. Or you can calculate the dot product and then just multiply that by the scalar c. All right, I'm going to scroll up a little bit, but I'll try to leave most of it there. All right, let's do that. All right, so let's take a look at some examples. Let's just do a basic. Well, first let me define u and v. Look for a good one. All right, so we'll do a basic dot product just to show you that for number one. And for number two, we're going to use our special rule number 4 here. I'm going to show you the comparison there. All right, so for the first one, we're just going to do the dot product of u dot v. So, there's a few different ways to approach this. If you feel comfortable, you could just go ahead and plug things in where they're supposed to be. If you feel like you need to organize your thoughts, do that first. All right, so I'm going to say that since u is -1, 3, that's going to be my u1 and u2. And then I have 2, -4. And that's going to be my v1 and v2. So the dot product says I multiply u1 and v1 and u2 and v2, and then I add those together. All right, so u dot v is going to be my -1 times 2 plus 3 times -4. Right? Then we just multiply and add. So I get -1 plus -12. So the dot product gives me -13. Oh, ha! Oops. That's not 1. -2. -2 and 12 is -14. And so just be careful with your signs, but it's pretty straightforward. Just multiply and add. Just get used to the pattern. Any questions about that? Normal dot product. Okay, so with that, you should be able to answer most, if not all, of the questions on the SGO. Okay, that was the last bit of information. But I want to show you real quick why number 4 works. So first, I'm going to do u dot u, and then I'm going to show you the magnitude squared. So using the u dot u dot product, okay, I'm going to have -1 times -1 plus 3 times 3. All right, that's using the dot product with u in itself. This gives me 1 plus 9, so I get 10. All right, so if I do u dot u, I get 10. So let's see if we get the same thing for the magnitude of u squared. Well, the magnitude of u is going to be the square root of 1 squared plus 3 squared, which is the square root of 10. So since the magnitude of u equals the square root of 10, if I square that, well, then I still get 10. Now, with this, it's, I wouldn't say there's a huge advantage of using one compared to the other. It would just be what you're more comfortable with. All right, so if you see u dot u and you have no problem just setting up a quick dot product equation, all right, you can do that. Or if you remember the rule here, oh, excuse me, oh, I'm tired today. Or if you remember this rule here, you can do the magnitude and then square the magnitude. So yeah, u squared is 10. Any questions there? All right.